Welcome to the next video. So in this video I'll be solving another KTU MoS problem. This is from civil S3 subject. So this is asked in 2017 December for 8 marks. So this is from the module 4. In module 4 it is from the bending equation, bending stress part. Okay. So a cantilever beam of span 3 meter and cross section 200 by 300 is to carry a UDL on the entire span. If the tensile stress is limited to 3 MPa, what is the maximum UDL that can be applied on the beam? Okay, so it's a straightforward problem. We have a cantilever beam. So this is a cantilever beam. We can draw support at any side. So let's say I'll draw support this side. This is a fixed support. We have 3 meter is the length of the beam. 3 meter is the length of the beam. The cross section is 200 by 300. So this is 200 by 300. Okay, and they're telling there is a UDL on the beam. So let's say it is, some value, some P kilonewton per meter. Okay, P or W, any term you can use. The tensile stress is limited to 3 MPa. What is the maximum UDL that can be applied on the beam? So what they're telling is, the tensile stress sigma T is 3 MPa. That is a maximum. Cannot be more than 3 MPa. Cannot be more than 3 MPa. Now cantilever beam, you have to imagine where tensile will be. Cantilever beam is going to deflect like this. It will deflect like this. Like this. Okay, so basically we are bending it in one direction. So top portion there will be tension and bottom portion will be compression. So this is a basic difference. If it is a simply supported beam, we have top compression, bottom tension. Cantilever, we have top tension, bottom compression. So this I hope you can imagine also this. Now the bending moment of a cantilever beam, this under UDL, it is better you remember this, but you can also derive this value. This is a what do you say? This is basically a UDL. UDL means the bending moment diagram will be parabolic. So it should look something like this. Sorry, it should look something like this. Okay, so this is a bending moment diagram. Bending moment diagram. The maximum value of bending moment will be at the end. This we can calculate. So basically, how do we find this? We will go through that. Some people, if you are able to draw this fast, this problem can be solved very fast. Otherwise, we will see how to draw this. Okay. So let's draw the cantilever. So let's say this is the support. So this support I can replace with reactions. Okay, so fixed support, there are 3 types of reactions that is possible. So there is a vertical reaction possible. So if I call this end as A, I'll call this as vertical at A. A horizontal reaction is also possible. I'll call this as horizontal at A. And a moment is possible. Moment I'll call as M at A. Then we have UDL. So first task we have to find is we have to find the reactions. Okay, horizontal reaction will be 0 because there is no horizontal force on the beam. So I can directly remove that, or I can put that as 0. Okay. Now vertical equilibrium. Vertical equilibrium equation is telling that so this beam is stable. That means it is not accelerating in the vertical direction, okay, or in the y direction. That means all the forces that is acting on the beam are balancing each other. So that is the meaning of vertical equilibrium. So that is nothing but summation of forces in vertical direction should cancel each other. All the forces should add to 0. Assume some direction as positive. I will assume the upward direction as positive. So we have what is upward force here. VA is there. Then we have the P here, force. P kilonewton per meter. So we have P is in downward direction. So total force will be P into length. Okay, so 3 meters. So this will be minus. So these are the vertical forces. There is no other vertical forces. There is a moment here, and that is not vertical force. There is a horizontal force, that is not vertical force. So this equal to 0. That means VA will be equal to 3P. So one reaction we have got. We have got one reaction. Now for second reaction, what you have to do is we have to find moment equilibrium or rotational equilibrium. Rotational equilibrium. Okay. So rotational equilibrium tells us the moment basically since it is this cantilever is stable, it is not rotating. All the forces that is causing moment, or all the forces that can cause rotation, are cancelling each other. So summation of all moments about any point on the plane should be equal to 0. What we will see, we will consider a point as A equal to 0. We have to consider one direction as positive. So for moment, we will assume clockwise as positive. You can also assume anti-clockwise as positive as you wish. Okay. Now about A I am finding. So there is an MA here. MA is a moment which is about A. So that we have to consider it is in anti-clockwise direction. So we have to write minus MA. Then vertical force is passing through the point, so it will not cause any moment. The UDL will cause a moment. It will be causing a moment in horizontal direction. Now you can see this UDL, the value of UDL, we can assume it to be acting at the center, or the resultant will be acting at the center. The value will be P into L. That means 3P. 3P will be acting at center. Center means it is 1.5 meter. So the moment due to this UDL is clockwise direction. About this point, it is trying to rotate in the clockwise direction. So 1.5 into 1 plus 1.5 into 3P equal to 0. So moment is nothing but 1.4 into 3. That means 4.5 P. Okay. So this moment will be the maximum value here. 4.5 P. That is a maximum bending moment here. Okay. So this whatever reaction is there, that will be the maximum bending moment at this location. For cantilever, it will be like that. Okay. So that is the value will be 4.4 times the UDL. I hope it is clear. Now, since we have got this, this is what all we need. There is another way of finding the bending moment diagram. So that also I will discuss, so that whichever way. One thing is, you remember this formula. So there is a direct formula here, so that also come handy. We can direct remember the formula. So moment will be equal to W or P into WL square by 2. Okay, so this is the maximum moment. So we can check here. It is same. This value also will be coming as same. Our W we don't know. P we don't know. L is 300. So 3 square by 2. So that is nothing but 4.5 P. Okay, so that comes correct. So this is one way of remembering this. Second is find the reactions. The reaction will be same as the maximum bending moment. And the third way, so if you know how to find the bending moment, then you can skip to the part where I am doing the calculation. The third way of finding bending moment is you cut a section here. So this is UDL, only one load is there. So that means so this is P, this is 3 meter. Okay, for cantilever, so this, since there is only UDL, any portion you assume x to be from this direction. So this is x is equal to 0. This is x is equal to 3. Okay, so we are assuming like that. Now cut a section here. So let's say I'll cut a section here, anywhere xx. So this section can be anywhere from 0 to 3. Okay, so I'll just isolate that portion. So this is P. This distance I'll call as x. Okay, and here we can have a moment and a shear. Okay, so right hand side is what I am drawing. So right hand side, the convention for positive moment is clockwise, and sign for positive shear force is upward. Okay, so this is so what I have drawn here is the internal forces. So for a beam, there will be two internal forces, a moment and a shear. So if there is an axial force on the beam, there will be an axial force also. Since there is no axial force on the beam, we don't have to draw that. So this is the internal moment here. This is the moment that is coming at this point. Now you can see x is from 0 to 3. The range of x is from 0 to 3. X can be here, any point up from 0 to 3 because the load is constant. Everything is constant in this section. Now equilibrium we can find. So this point I will call as O dash O. This point I will call as O. So summation of moment about O equal to 0, clockwise positive. And the reason for this is since this beam is in rotational equilibrium, it is not rotating. This portion of the beam also will not rotate. Okay, so that means this portion of the beam also is in rotational equilibrium. So there are which are the forces acting on the section? So there is a UDL, there is a moment, there is a shear force. Okay, all these are keeping it in rotational equilibrium. Now we will find rotational equilibrium about O. Okay, the reason for that is we can avoid this shear force now. So at that O we have a clockwise moment, so that will be positive plus m. Then we have a clockwise UDL. So UDL, the value of UDL is nothing but, so this I will write, the net value will be P into X. Okay, it will be acting at X by 2. This distance, total X distance is X, this will be acting at X by 2. Okay, so force into distance will give me P into X by 2. So you can see it is also clockwise, so it's also plus. Okay, so this equal to 0. So m equal to minus P x square by 2. So minus means the negative sign indicates it's sagging moment. Okay, so it's negative. So this is the moment we want. Now put x is equal to 3 meters to get the moment at this location. Okay, so that means it is nothing but m equal to minus P into 309 divided by 2, that is minus 4.5 P. Okay, so now here you observe that if you do this method, you are getting the sign. With the sign you are getting. So here and all it is little confusion with the sign, but this moment is nothing but minus 4.5 P. Okay, now I have written only the magnitude here. The actual value will be minus. Will be minus 4.5. This also will be minus 4.5. Okay, because I have not considered the sagging consideration. The best way is this, but fastest way is this. If you can remember this formula, this is the fastest way to solve this. Now you can see this equation is a parabolic equation. Power of x is 2, so that means this curve is a parabolic curve. Okay, so either way, any three of this method you can adopt and find the maximum moment. Why we want maximum moment? Because the bending stress will be maximum where the moment is maximum. Okay, so I want to find where the moment is maximum. So any bending stress formula, when they ask you to find the stress or when they ask you to find the load, always you have to find the maximum bending moment location, because at that location we will have maximum bending stress. Now once we have found that, we can say, so this is this section, the section just near the support. At the support will have the maximum bending moment. The value of bending moment will be 4.5 into P. Okay. Now what will be the variation of bending moment? So that bending stress, so that also we will just quickly draw. So this is the cross section. This is the center line, neutral axis. So for neutral axis, we know neutral axis, and this is hogging. Hogging means top portion will be in tension. Okay. Top portion will be tension and bottom portion will be in compression. This is a neutral axis. So for rectangular section, because of symmetry, this distance will be half of the depth, that is 150, and this is 200. This is again 150. Okay. So stress and bending moment, how is it related? By bending equation. So bending equation, if I write, bending equation, if I write, it is m by I equal to sigma by y equal to E by R. So the last portion I don't need, so I'll use only M by I equal to sigma by y. Now how does it give? So at a given section, we know M, we can calculate the I about the neutral axis. With respect to the y, we get different sections. Now what is y? Y is nothing but the location of the point where we want to find the stress. So if you want to find stress at this point, okay, so put y value. So let's say this is 150, you want to find stress at 75 mm from the neutral axis. So this y is always measured from the neutral axis. So from 75 mm from neutral axis, we want to find the value of stress. So what do you do? Put y equal to 75, m is constant in this section, m is 4.5 p, I is also constant for a section because section is constant throughout the length. We get the value of stress at this point. Put y equal to 150, you get the stress at this point. Put y equal to 150 here. Again, one convention is don't think about the sign of y. It's okay. If you understand which is tensile, which is compression, you just have to, you don't have to worry about the convention, sign convention, direction of sign convention of y. Okay. Now for this is the maximum tensile stress. What is given here is the maximum tensile stress is 3 MPa. So maximum tensile stress is at the top. Okay. So for maximum tensile stress, the value of y will be equal to 150. Okay, you can see from neutral axis it will be at the 150. So maximum compression also will be same here because it's a symmetrical section. There is no changes here. But let's say this is the max value of y. So it is given, sigma is also already given. So we'll just substitute values. Now what is the value of I? We have to find I equal to BD cube by 12. It is a I value about neutral axis. So nothing but B is 200, D is 300 cube upon 12. So this gives me, so we just quickly calculate this. 200 times 300 cube by 12. So this is, so 1, 2, 3, 4, 5, 6, 7, 4.5 into 10 raised to 8. 4.5 into 10 raised to 8 mm to the power 4. Okay, I'll just quickly cross check. Okay, 4.5 into 10 raised to 8. This is 4.5 into 10 raised to 8. Now, substitute in this bending equation, m by I, value of m is 4.5 p. So 4.5 p. So now this is 4.5 p. This is in kilonewton meter. This I should have told you earlier. This is in kilonewton meter. Because all the units that we are taking is, this is meter. So this is also we are taking kilonewton meter. Okay. So 4.5 p into 10 raised to 6 for converting it to Newton millimeter. By I is 4.5 into 10 to the power 8 m by I equal to sigma. Sigma, what is the value of sigma? Sigma is given as 3 MPa. Maximum stress should be 3 MPa. 3 divided by 150. So there is only one unknown here, that is P, which we can find the value of P here. So we'll just quickly calculate. So we can see that here 10 raised to 6 and this we can cut. So 2 is remaining. 4.5 and 4.5 will go. So P by 100 equal to, so this comes out to be, let's say, so we don't need a calculator also to solve this. So P by 100 equal to 3 by 150. So 3 by 150 is 1 upon 50. Okay. So this gives me P equal to 100 by 50 equal to 2 kilonewton per meter. So this is the UDL. Okay. This is the UDL which you have to apply on the beam so that the stress is 3 MPa. Now if you increase the UDL, what happens? This is the maximum stress that can happen, can reach. If you increase the UDL, the moment will increase automatically because it's 4.5 times P. When the moment increases, the stress exceeds 150, exceeds its value, that is 3 MPa. So when the moment the stress exceeds 3 MPa, it will break. It will break in tension. Okay. So whatever stress, if this UDL is less than 2, let's say 1.5, the maximum stress will be less than 3 MPa at the top. So this is how we solve this problem. Now this problem I might have taken a little too long because I have mentioned you 3 different ways of calculating the maximum bending moment. Cantilever with the UDL, you can either remember this, you can find the reaction, that will be the maximum bending moment. So if there are multiple loads also, if you find the maximum reaction, that means moment reaction, that will be the maximum bending moment. Or you can use this sections. Now, if there are multiple loads, you may have to calculate different sections. I feel this is the safest example for a cantilever. If you can find the reactions, then that will be the maximum bending moment. You can go with that. Okay, so that's it. I hope some of you have understood how to solve this kind of problems. Okay, thank you. We will again solve another problem in the next video.